Thank you, and good afternoon to everyone. So today's topic, we're going to talk about seals and migration. And the first image here is from lecture number 2, where we talked about clay elements, the source rocks, hydrocarbon migration, and then reservoir trap and seal. And so highlighted with the white ovals, we'll talk about hydrocarbon migration, and we'll also talk about seals for conventional traps. This is something that I have shown in lecture 7 and also lecture 8. There are 4 essential elements. When we're trying to find oil and gas, we need a source rock, we need a reservoir rock, we need seal, and we need overburden so that we have a certain degree of depth of burial. For the processes, we have processes related to how the trap formed. And then in terms of hydrocarbons, processes about hydrocarbon generation, migration, and accumulation. So today we'll talk about the sealing rocks, and we'll also talk about hydrocarbon migration, and I guess you could say also accumulation. So what is a hydrocarbon seal? It's not the little critter that you might go to SeaWorld to see. It is a unit, and it has to have low permeability so that it impedes the escape of hydrocarbons from out of the reservoir rock. Some of the more common seals are any type of evaporite, salt type deposit. Chalks can be good seals, and deep water shales can be good seals as well. The analysis of seals involves the assessment of how thick they are, what lateral extent they have, and we are trying to quantify how effective a particular seal will be. And we'll talk about that in the next few minutes. Here's a little diagram. We have a source rock kind of in the purple color. We're generating hydrocarbons. They're migrating up the fault. They get into a carrier bed, porous permeable. In this case, it's meant to represent a sandstone. We have a trap, an anticlinal trap, and we have a free gas cap, and we have an oil leg, and within the oil, we may have some dissolved gas. And then the gray layer is the sealing lithology that's going to keep the hydrocarbons within that trap so that all of it doesn't percolate up to the surface. A couple of examples of types of traps that are common, again, in conventional fields. We have an anticlinal trap where we have a local high. We are showing here a gas cap and an oil leg. Again, the sealing rock or the cap rock is in gray. Here we have a normal fault. We have a trap on the downthrown side. And for the gas and the oil to accumulate on the downthrown side, that means that the fault has to be a sealing fault in terms of hydrocarbon. We can have stratigraphic traps. Here we have an unconformity, and oil and gas is trapped beneath the unconformity, given that on top of the unconformity, we have a sealing lithology. And here we have, instead of a normal fault, we have a thrust fault or a reverse fault. We can trap oil and gas on the hanging wall or within the footwall. And then I've added one more, that is traps beneath salt. So if we have a salt feature and maybe it has an overhang as shown here, we can trap oil and gas beneath salt in the overhang or on the flanks of the salt dome as well. These types of salt traps are very important these days in the deeper water Gulf of Mexico exploration, development, production. So a critical question we ask is, given a particular trap, how much oil or gas can it hold? Another way to express the same question is, what is the controlling factor for the hydrocarbon fill in this trap? There are 3 general controls that we consider. One is the synclinal spill point, and I'll show some examples of that. Another is a fault leak point. And then the third is what's the sealing capacity of the sealing rocks. How thick of a hydrocarbon column can they hold in place? And so we'll look at these three in the next few slides. So a synclinal spill point, it's the structurally lowest point in a hydrocarbon trap that can retain hydrocarbons. Once the trap has filled to the spill point, further storage or retention of hydrocarbons in that particular trap will not occur because we have no more reservoir space. The hydrocarbons will spill through that low point, the synclinal spill point, and continue to migrate until they are trapped elsewhere. And I use this diagram in lesson 2 where we have a gas cap and an oil leg. This is the synclinal spill point. It's the lowest point at which we can still hold the hydrocarbons in place. And if we generate more hydrocarbon than the trap can hold above that spill point, the excess hydrocarbon will spill, in this case, towards the right and go further up the migration path or up dip. Here's an example. This is from the Middle East. Tengiz is a carbonate reservoir. It's a very major reservoir of oil. I lost the pronunciation. Korolev is another carbonate reef. I'm not sure where the hydrocarbon kitchen is, but let's say it's off to the left as the green arrow is showing. In that case, Tengiz would fill up first with oil. When it reaches the lowest depth contour within this low point or this saddle or this incline, if we add more hydrocarbon to it, it will start to fill up the other structure further up dip and along the hydrocarbon migration pathway. We can also have fault leak points. Faults can either trap or they can leak hydrocarbons. If a fault is a good hydrocarbon seal, it'll prevent the hydrocarbons from flowing out of the trap. Some faults will only inhibit the flow. They don't totally seal on a geological time scale. But when we're talking about a production time scale of 10 or 20 or even 50 years, they may seal. In some cases, faults will seal oil, but they won't seal all of the gas. If we have a non-sealing fault, that can serve as a migration pathway. So I have two diagrams here. If the fault leaks, as in the diagram on the left, we'll fill this trap B up with gas and oil, and this will be the leak point where the hydrocarbons will be able to move up the fault and continue until it escapes up the migration route. If the fault seals in this case, then the limit of hydrocarbon is not controlled by the top of the reservoir where it intersects the fault. It may be controlled by a different synclinal spill point, a different fault leak point, or maybe just the volume of hydrocarbon that has been generated and migrated into trap B. Here is a structure map showing a couple of faults over a high block. If all of the faults seal, then we would look for synclinal spill points to define how much hydrocarbon can be contained. And so we'd have one compartment here, a second compartment here, a third compartment here. If, however, I'll zoom in where the magenta box is, if the faults leak, then we have to look for closing contours within each fault block, and we can see that the eastern compartment, the central compartment, and the western compartment have much less volume of oil than in the case if all the faults are sealing. This is an example of that I pulled off of the internet. Again, it's a structure map, and someone has interpreted that the fill level is down to the dashed magenta line, And if this is the true distribution of the gas, we could ask, does fault Q, and that would be this fault here, does that seal or does that leak gas? And the way it's drawn, because these contours run into the fault, this fault Q and this fault as well would have to seal gas. If the fault Q allowed hydrocarbons to leak, at least on a geological time frame, then the red contour would be the maximum extent that the gas could occupy within this particular trap. The quality of the seal depends on the buoyancy of the oil or the gas, and both a combination of gravity and the resistance of the overlying unit to have its fluids be replaced by the oil and gas. So we need low permeability rocks to have a good seal. The hydrocarbon wants to escape due to the upward force of buoyancy. The opposing forces, as I mentioned, are gravity and the resistance of the fluids in the overlying rock to be replaced. So if we have a drop of oil, if it's in a reservoir, we have sand grains with a lot of pore space and good permeability, connectedness of the pores. The oil will migrate through this up to the top of the reservoir, and if there's a sealing lithology above it, it will then be trapped. So here we have, this is meant to be a shale overlying the sand reservoir. The shale mineral grains are more plate-like. That makes the porosity and permeability much less, and so there may not be enough buoyancy force to overcome gravity and the resistance of the water in the shales to get replaced by either gas or by oil. So a few things to note. Pressure on the seal increases as the thickness of the oil or the gas column increases. So here we have the diagram. We have a certain thickness of gas. If that gas column gets thicker, it may put enough buoyancy pressure on the seal that it will cause the seal to fracture and allow some of the gas to leak. So the upper limit on the thickness of the hydrocarbon column that it can hold in place is something that we try to determine. Once that upper limit is reached, the seal can fracture and leakage can occur until the forces are back in balance. Gas is much more buoyant than oil because it's got a much lower density. And so it is possible for a particular seal to leak gas while it can hold the oil in place. So in the diagram here, what I'm trying to represent is that if we add more gas, it will leak through the top seal because the pressure with the gas height, the gas column height is sufficient to allow it to break through, but oil would not leak through this seal. It would spill at a synclinal spill point. So fault seal analysis is an important consideration for us, especially in exploration. A particular fault can either be sealing to hydrocarbon flow or it can be a conduit. We've seen in a couple of examples that the hydrocarbon volume will differ depending on whether we consider the fault to be sealing to hydrocarbon or leaking to hydrocarbon. So fault seal analysis is a very important part of sizing a prospect or a field. We don't have time to go into too much detail, but I wanted to touch on two common methods that are used to consider fault seal. One is juxtaposed lithology, and the other is fault smear gouge. So with juxtaposed lithology, we may have a succession of sands and shale layers that are offset by a fault. Hydrocarbons may be able to leak across from a porous sand if it's juxtaposed against either the same sand body, as sand body A is juxtaposed against A, we have the possibility for cross-fault leak. B can cross-fault leak as well, and so can C. Or we can have a different porous sand that could cause us to have cross-fault leak. So here we have a fault with more offset. Top of A drops down to here, top of B drops down to here, and then C would be further down. If we have sand C juxtaposed against sand B, then we can have leakage from the right side sand C level to the left side B level. Here's a piece of seismic, and I've colored in yellow where the interpreted sands are, and we'll put a little shading on that. And so here we have sand that's juxtaposed against a shale, and so that would be considered to have a lower chance of cross-fault leak. Down here we have some sand juxtaposed against some sand at the very top of this sand, the very base of this sand, and so that has a higher chance that we could have some cross-fault leakage. So if we had hydrocarbon in this sand, if we are juxtaposed against shale and the fault zone is not porous and permeable, then we would consider this to be a sealing fault. However, the lower sand, it can have a sand-to-sand juxtaposition here, and so we might have cross-fault leak. We could start to fill this thing up until it reaches a synclinal spill point, and then we would spill further off to the right. One of the methods that we can use to examine cross-fault leak is to develop what is called an Allan diagram. So here's a base map. There's a fault. High side is on the west and the low side is on the east. Line A to A prime is shown here. And so we have a reservoir quality sand that's been down thrown across the fault. What we can do is we can construct a cross section on the high side of the fault, B to B prime, and also on the low side of the fault, C to C prime. And so here it's B to B prime, and here's where we think the porous reservoir quality sands are. Here's the low side, C to C prime. Here's where the sands are. And then if I take those two and superimpose them, I can look for places where sand on the high side touches or crosses sand on the low side, and this then would be a potential cross-fault leak. And so if we are generating and percolating hydrocarbons, it gets into the low side sand, it will move up dip, and it will start to fill the high side trap. And when it gets to this point where we have sand juxtaposed against sand, if we continue to generate hydrocarbon, it would not have any more space or room within the high side trap, and it would continue to migrate further towards the right or the east. Fault smear gouge, as we have material that is offset along a fault, we can get some of that material entrained within the fault region itself. Faults are typically not a single cut, but a series of cuts. And so we can get the entrainment of shale, and in the diagram, blacks are representing shales. We can get shales that get smeared within the fault zone. And so depending on how much shale is smeared, the fault may become impermeable to flow of hydrocarbons. Oops. So we can calculate what is called the shale gouge ratio, SGR. And so here we have sand A, and it's offset down through the fault to this position. And so we can consider what layers have been smeared against each other. There's an equation here. We take the volume of shale from layer 5, so this guy, multiply it by the thickness of layer 5, and then layer 6, and then layer 7, and we take that addition and divide it by the vertical offset. That gives us a quantity that's referred to as this shale gouge ratio. And the higher the shale gouge ratio, the more likely it is that the faults will seal hydrocarbons. Various companies have done this type of analysis with known fields, with known leak points, either spill points or cross-fault leaks. And so different companies have different numbers, but there is some threshold number that a company would use. If the shale gouge ratio is greater than 0.6, then they would consider the fault to be most likely sealing. We can also look for geophysical evidence for how filled a particular trap is. A sand that has either gas or oil in the pore space will have a significantly higher reflection coefficient than sands with water or silts or shales. And so in a number of cases, we'll see an anomalously high seismic amplitude that tells us what the extent of the hydrocarbon fill within a trap is. So here we have an anticline. The colors are showing high seismic amplitude along the reflector that was mapped as the top of the reservoir. The really high amplitudes are yellows, oranges, and reds, so located here. A well was drilled just outside the high amplitude and it was dry. A well was drilled here to the west of this fault and it encountered a hydrocarbon. And so if we're trying to assess should we drill at this location or not, the presence of the high seismic amplitude would suggest that there's a very good likelihood that we'll find hydrocarbon in this well as well. If the high amplitude values conform to the crest of a structure, that's a direct hydrocarbon indicator, a DHI, that we'll talk about later on in these series of lectures. And if something like seismic amplitude tells us how filled a trap is, that can tell us a lot about what might be controlling the amount of fill level, whether it's a synclinal spill point or a fault leak point, or maybe the sealing capacity of the overlying seals. So let's move on to hydrocarbon migration. Hydrocarbon migration is the movement of oil and gas molecules in the subsurface. The primary driving mechanism is pressure-driven buoyancy. Lighter molecules move to lower pressure conditions. Normally, this is a vertical movement, but if we are in areas where part of the section is overpressured, we can have some non-vertical migration. So hydrocarbon migration can be along porous carrier beds, or it can be up through fault zones or through fracture networks. So here's the diagram I showed a little earlier. We have hydrocarbon moving up the fault and charging the reservoir quality sands that have a trapping geometry at the crest of the anticline. So we'll talk a little bit more about hydrocarbon migration. There are two types of migration that we talk about. Primary migration, that's the percolation of oil and gas molecules out of the source layers into more porous carrier beds. There can be a delay in geological time between when the source starts to generate oil and gas molecules and when the oil and gas starts to leave the source rocks and gets carried in the carrier beds. And if you're using migration modeling software, this delay time is something that the user can set. So primary migration is getting out of the source rocks. Secondary migration is once it gets out of the source rocks, how does it get to where it is trapped in an economically viable quantity. It can move in silt layers or in sand layers, and the layers do not have to have reservoir quality sand, it's the same quality as reservoir quality sands. They can be lower porosity and lower permeability because we have millions of years for the hydrocarbon to move through the subsurface up to the traps. So let's consider a drop of oil generated in our source rock, which is shown in gray here. The primary migration would be the tortuous path to get out of the source layer itself, since the source is typically in fine-grained rocks such as shales. It will then start secondary migration, eventually get to a more porous permeable layer, and then it will move up dip to the crest of an anticline. We'll assume that above the yellow layer, we have a less permeable lithology, so it controls or confines the hydrocarbon movement to the yellow carrier bed. If we're doing basin modeling, trying to predict hydrocarbon migration, we'll look for regional sequences that we can map, and ones that we think either are carrier beds or could act as carrier beds. And then we generate depth structure maps, or we may deal with time structure maps for the tops of these sequences to try to understand how the hydrocarbon might migrate. So we might generate some hydrocarbon here. The primary migration gets it out of the source. It reaches the top of the carrier bed. We have a more less permeable, more sealing lithology above the yellow, and so it moves up dip to get to the highest point on the structure in trap W. Similarly, if we generate a molecule here, it will move up into trap E. And then we could generate oil, and if it happens to reach the carrier bed in the syncline, then there's a 50% chance it'll go to the west and fill trap W, and a 50% chance that it will go to the east and fill trap E. So it's very similar when we talk about rain falling on a continental divide. In this case, the continental divides are the drainage basin separators. When we're talking about hydrocarbon migration and primarily vertical movement, the synclines become our drainage divides. So we can model what would happen at the top of a carrier bed. This is a 3D rendition or view, and we have several drainage divides which are shown in blue. We have regions with dip up to particular culminations or highs or crests or anticlines. The light red is meant to represent gas caps. The green is meant to represent oil legs. And the black arrows are meant to represent the secondary migration flow paths that we would predict given the particular structure. So this is the 3D view. We can also look at that as a map view. And again, the blue would be the drainage divides. The black arrows are the secondary migration paths at the tops of carrier beds. And then the culminations are where hydrocarbons would accumulate, gas caps and oil legs. So let's consider a hypothetical area where the red would be a drainage divide. It would be a syncline defining a particular mini basin. The highest point in this mini basin is located here. And so any hydrocarbon that would be generated within the yellow shaded region would percolate up and try to fill this particular trap, this particular high or crest. We also have to worry about hydrocarbon not just filling a trap, but also spilling from it. And I like to use analogies. So I have here represented an aquarium. I have a 12-ounce container. We could call it a glass. that's inverted. It's filled with the aquarium water, and then I have an air pump. And if I turn the pump on and it pumps in 3 or 6 or 9 or 12 ounces worth of air, the air being less dense will rise to the top of the glass and displace the water. Now, what happens if I continue to pump air into this particular container? The excess is going to spill out the sides. And if there is another container, another trap, it will start to fill that trap up with the air. So the same thing will happen in a hydrocarbon system. If the deeper trap is filled to its capacity, it can no longer hold additional oil and gas, but more oil and gas is supplied to it, it will spill. The spilled hydrocarbons will move up the migration route and possibly fill a second and maybe even a third trap. So here we have the hypothetical trap 1, mini basin 1 with an anticline. Let's say there's a synclinal spill point, and if we fill to this level, it would start to fill the anticline in mini basin number 2. There's a fault at the north end of mini basin 2, and let's assume that this is a leaking fault. And so at the leak point, a hydrocarbon would move further up dip to the anticline in mini basin 3. So this is the deepest part of the migration pathway. This is intermediate, and then this is the highest. So if our oil kitchen is down to the south and we start to generate oil, we'll start to fill trap 1, and we fill it some more, and we fill it some more until we're at the synclinal spill point. If we continue to add oil, it will spill into mini basin 2 and start to collect at the apex of the anticline in mini basin 2, and that will continue until it gets to the fault spill point at the near the crest of the structure in 2, and it'll start to leak into, or spill, I'm sorry, into the the crest in mini basin number 3. So we have software that does all of this for us. We have to input a lot of information, grids about different surfaces, the source rock and its characteristics and how it's generated oil and gas over time. It turns into a huge accounting exercise. First, we'll define all the drainage polygons. We'll calculate the volume of oil and gas that can be generated within each local polygon, the local fetch. We'll calculate the volume that each trap in each of the polygons can hold. And then we start to model hydrocarbon migration. We start at the deepest drainage polygon and consider if the deepest trap is filled to spill or not. If it's filled to spill, then the excess hydrocarbon is added to the local fetch for the next shallower trap. And if then that gets filled, it spills or it leaks into the one that's further up in the migration pathway. So we progressively work from deepest to the shallowest combinations of polygons and traps. So I have an example here from the North Sea. This is work I did with a gentleman named Oyvind Silta back in the early 90s. The blue here is the drainage polygon. We used maps, and the maps were gridded, and so that's why it's a rectilinear shape. 1, 2, 3, 4, 5 is the trap identification number. Each drainage polygon has a culmination, a high point. It also has a spill or a leak point. We calculate how much hydrocarbon is generated locally. We consider if there's been spillage into it from a deeper polygon. And then we start to worry about how this particular trap is filled in terms of free gas or oil with dissolved gas. and if the trap is filled to spill or leak point, where was that extra hydrocarbon spilling or leaking to? So we have local drainage, how much hydrocarbon is generated within the local fetch area, how much of that was expelled. We worry about primary migration and then secondary migration. We can also worry about hydrocarbon loss during migration. And then we can consider several different drainage polygons. In this case, this is the deepest one. This has a gas cap and an oil leg. We've spilled some oil with some dissolved gas into here. We've also generated some oil and gas within this polygon. Some of the oil has spilled out of here up to this culmination. This particular polygon, the source rock is immature, so we have no local generated hydrocarbons. And so whatever gets into trap 37301 is going to be spilled. And we can get spilled oil from this direction, and we can also get spilled oil from this direction. I'm going to use some real field examples now. Huldra is the deepest of the traps. Oseberg is midway up in the migration pathway, and Braga is the shallowest. And Braga is in an area where we don't have any local hydrocarbon generation. We only have spillage from deeper down. So Huldra, the deepest one, the maximum oil content has been released. We've added excess gas, and so we're spilling oil and retaining gas in Huldra. Oseberg is close to having its maximum oil content. It's getting locally derived oil plus spillage from deeper drainage areas, such as the Huldra drainage area. And then Braga, there's no local hydrocarbon generation and drainage. It only contains spilled oil and gas. And so on the right, we have, through geological time, the oil fill for these three fields, the free gas field or the gas cap, and then, I'm sorry, the free gas cap is down here, the total gas is in the middle. And so we can look at the deepest one, Huldra, and the amount of oil increases until about 20 million years ago, and then it starts to drop. And it's dropping because the total gas in Huldra increases dramatically. And so this loss of oil is attributed to the spillage of the oil as the gas has been flushing the oil out of the deeper trap. Oseberg has received oil and it's almost at its peak amount. And it had some free gas, but then that free gas has been dissolved within the oil as it's received more and more oil. And if we look at Braga, it has no oil until about 20 million years ago, and then it starts to increase, and all of this is spilled oil. There is no locally generated oil because the source rocks within the Braga drainage area are immature. We can also see that Braga is receiving some gas, but there is no free gas or very little free gas. There's no gas cap. All of this gas is dissolved within the oil within Braga. So that's just a very quick look at some of the types of modeling that we can do, some of the conditions that we can simulate. And if these weren't known fields and these were prospects, we could do the same sort of analysis, trying to understand the different fill level for different fields. So this slide has references to some of the images that I have on the previous slides. Many of them are from internet sites. The last North Sea example is from a publication that was put out in 1993. So we've covered now seal and migration. We've talked about the different play elements, source reservoir, trap seal, migration. Thursday, we'll start talking about seismic interpretation. We'll talk about new ventures, well seismic ties, seismic acquisition, processing, and get into more and more into the seismic interpretation and seismic analysis. So that's the conclusion of my prepared remarks. I'll turn the podium back to Dr. Sume and see if there are some questions from the audience.
Thank you, Fred. There aren't any questions that have come through yet, but I actually had one myself because you've given a great overview of all the different types of modeling that you can do to best understand your hydrocarbon play. And I was wondering, as we kind of move up the food chain regarding in the corporate structure, you know, when you're looking at this, these different models and trying to understand this, the economic impact of, you know, what's going on geologically, how does it usually translate up within the oil industry? Does that make sense? My question makes sense.
Yes. A lot of times what managers like to see is what we call the most likely or most probable scenario. Our best educated guess is that there's going to be X number of cubic feet of gas and Y number of barrels in a particular structure that we're thinking about drilling. They also like to say, well, how small might it be? And then on the other hand, how large might it be? And so we talk about a high side case, that's the optimist. And then we talk about a low side case, that would be the pessimist. So as an example, one of the slides I showed had a fault Q, I believe it was, and we showed what the hydrocarbon fill would be if the fault sealed. That might be close to a high side case. And then we showed what would the size of the field be if the fault leaked, and it was maybe 10 or 15% of the amount if the fault sealed. And so that's just kind of a quick example of how you might consider if everything is working favorably to giving you a higher volume, how big might it be? And then if things are not quite so favorable, how small might it be?
Oh, sorry, my mic wasn't on. All right, thank you, Fred. So there weren't any questions today, but since it's already 2:47 on my time, it's probably best to end the webinar anyway. So thank you everyone who attended, and we'll see you on August 3rd for seismic interpretation. All right, have a great afternoon, everyone. Take care. Bye.
Thanks, everyone. Bye-bye.